On March 18, 1993, the 0.4-meter Schmidt telescope at the Palomar Observatory took pictures of space. This was done as part of a routine asteroid survey, a search for objects that could pose a risk to Earth. On March 24th, astronomers Carolyn S. Shoemaker, Eugene M. Shoemaker, and David Levy examined a pair of photographs. The trio had collaborated before, and together they had discovered several comets. And though it wasn't their intention this time, they were about to find another. In the photographs, the trio saw this. The images showed a 13.8 magnitude comet, far too dim to be seen with the naked eye, but it looked very unusual. It had the appearance of, as they wrote, a dense linear bar, oriented roughly east to west, and no central condensation was visible, but a fainter, wispy tail extended north of the bar and to the west. Upon its report to the appropriate authorities, the comet was given the name Shoemaker-Levy 9, designating it as the 9th comet to be discovered by the trio of astronomers. It received a more formal name, P/Shoemaker-Levy 9, when astronomers realized that it completed one orbit around the Sun every 17 years. The P at the front of the name tells us that it was a short-period comet. Short-period comets are ones with an orbital period of less than 200 years. 2 nights after the initial discovery, the object was confirmed through Spacewatch CCD scans by James Vernon Scotty at the Kitt Peak National Observatory. These scans revealed a long, narrow train of objects. In other words, what was initially thought to be one object turned out to be many. At least 5 that could be seen in the scans. So why was the comet fragmented? Why, rather than one solid object, did it appear to be a train of many pieces? Aside from its unusual appearance, the comet's location was also a point of interest. Following the comet's discovery, a number of pre-covery observations came to light. This just means that scientists dug up images or instances of the comet being observed but not formally recognized. These pre-covery observations made it possible for Brian G. Marsden, the director of the IAU Central Bureau for Astronomical Telegrams, to map Shoemaker-Levy 9's orbital parameters. And this revealed something that would turn out to be absolutely crucial for the comet's history and future. Marsden's announcement of the comet in the IAU Circular 5725 included the following remark. The comet is located some 4 degrees from Jupiter, and the motion suggests that it may be near Jupiter's distance. As more observations of this comet were made and its orbit became more highly refined, it became apparent that it wasn't just near Jupiter, it was orbiting Jupiter. The IAU Circular 5726 on March 27, 1993 contained the first orbits determined for the comet. Marsden used 9 positions obtained on March 24th, 26th, and 27th to compute 2 different orbits, one parabolic and one elliptical. Both orbits indicated very close approaches to the tops of Jupiter's clouds. The parabolic orbit indicated a close distance of 0.31 AU on March 30th, 1993, and the elliptical indicated a distance of 0.04 AU on July 28, 1992. More pre-covery positions came to light, and more observations of the comet were made. These eventually allowed Marsden to rule out the parabolic orbit, as it was no longer viable as of the IAU Circular 5744 on April 3, 1993. In the same announcement, Marsden provided a revised elliptical orbit that indicated a close approach of just 7/1000ths of an astronomical unit from Jupiter on May 16, 1992. Over the next month and a half, even more positions were obtained. In the IAU Circular 5800 on May 22, 1993, Marsden provided another greatly improved orbit for the comet. This orbit indicated that Shoemaker-Levy 9 passed a mere 0.0008 astronomical units from Jupiter on July 8, 1992. This distance from the massive planet was so small that it caused the comet to be torn apart into around 21 different pieces. Why exactly did this happen? All things with mass have gravity. Stars, planets, moons, even you and me. Because we have mass, we have gravity. Something with greater mass will exert a greater gravitational influence on other objects. However, distance also affects the strength of a gravitational pull. That's why we, in the solar system, aren't affected by the gravity of some other star out there, like, let's say, Betelgeuse. We're just much too far away for it to pull on us. Now, let's take something that orbits something much bigger than it. For example, Earth's moon. One side of the moon is closer to Earth than the other, and thus the closer side experiences a greater gravitational pull than the far side. These are tidal forces. The difference between the gravity on the near side of an object and the gravity on the far side of an object. And this is where the Roche limit comes into play. A Roche limit is the distance from a large body at which the tidal forces on a satellite become so powerful that they overcome the gravity holding the satellite together. And because they're so much greater, the satellite, the smaller object, is torn apart. This is probably what created the rings of the planet Saturn. The rings lie within Saturn's Roche limit, so they could be pieces of a demolished moon or multiple objects that just drifted a little too close to the giant. This is also what will inevitably happen to Phobos, a moon of Mars. In millions of years, Phobos will draw close enough to the red planet that tidal forces will break it apart, potentially giving Mars its own ring. And this is what happened to Shoemaker-Levy 9. The comet probably orbited the Sun for a very, very long time. It likely originated as a short-period comet, and its path probably ranged from just inside the asteroid belt at perihelion to just inside Jupiter's orbit at aphelion. But at some point, its solar orbit was disturbed by the gravity of Jupiter, our solar system's most massive planet. This happened sometime between the mid-1960s and early 1970s. In the years following the comet entering a highly eccentric 2-year orbit around Jupiter, it made several close approaches to the planet. These approaches got closer and closer and closer until it carved a path deep within Jupiter's Roche limit, breaking it apart before it had even been discovered. Shoemaker-Levy 9 is estimated to have broken into around 21 pieces, although the exact number is hard to know. The imaging limitations of the time and dust obscuring the fragments made it difficult to find tinier chunks or tell if larger ones were actually multiple pieces. Regardless, each fragment was named after a letter, A through W excluding I and O. Fragment Q near the center was identified as the brightest and likely the biggest. It was very uncommon to see a comet broken into multiple fragments like this. More unusual still was observing a comet that had been captured into orbit around Jupiter. But Shoemaker-Levy 9 still had one more trick up its sleeve, one more surprise for the astronomers studying it. In May of 1993, Marsden predicted that the comet's future trajectory would carry it within just 28,000 miles of Jupiter's center. Not the tops of its clouds, but the center of the planet. This distinction is critical because, well, Jupiter's radius? It's over 43,000 miles. And you don't have to be very good at math to know that 28,000 is a fair bit smaller than 43,000. This prediction sparked a single, indisputable conclusion. Shoemaker-Levy 9 was going to collide with Jupiter. This was no small event, no meaningless prediction. It marked the first time humanity had predicted such a collision between two objects in the solar system more than a few minutes before it happened, and it was our first opportunity to observe such an event. The impact was predicted to shed new light on both Jupiter and the comet. It could pull out material from deep within the planet's interior and inject it into the upper atmosphere, giving astronomers new insights about Jupiter's unexplored depths. We could learn more about the dynamics of comets and how they evolve. Astronomers were understandably excited and thrilled by this opportunity. Collisions between bodies in the solar system were way more common far in the past, before humanity was ever around to observe them. And sure, we've seen meteors strike our own planet, but the chance to watch something hit Jupiter was monumental. But the impact wasn't going to be easy to observe. Jupiter would be an entire 534 million miles away from Earth when the impact occurred, and this meant the effects would be very difficult to see. And there was still one more frustrating complication. The fragments of the comet would approach from Jupiter's south at around 130,000 miles per hour. They would collide south of the planet's south temperate belt at around 45 degrees south latitude. This placed the impacts on Jupiter's far side, where telescopes on Earth could not see. There was still a silver lining, though. Jupiter rotates extremely quickly, around 10 hours on average, which is the fastest rotation for a planet in the solar system. This meant the aftermath of the impacts would come into view just a few minutes after they occurred. Such an opportunity as this couldn't be passed up. Astronomers prepared to watch the fragments of Shoemaker-Levy 9 crash into Jupiter's atmosphere. Ground-based skywatchers hoped to see flashes of the impact reflected off of Jupiter's innermost moons. The Hubble Space Telescope watched Jupiter and the comet closely both before and after the event. The Galileo spacecraft was still on its way to Jupiter. With its arrival predicted for December of 1995, it wasn't going to make it in time to make closer observations. But it had direct visibility of the impact flashes from a distance of just 150 million miles. The Ulysses probe, designed to circle and study the sun, also had line-of-sight visibility for radio observations about 240 million miles south of Jupiter. And even Voyager 2, which at that time was about 4.1 billion miles away from Jupiter, would still be able to watch from afar. And so, all eyes were trained on Jupiter. On July 16, 1994, Fragment A was the first of the train to penetrate Jupiter's atmosphere. At the time of collision, it was traveling at 35 miles per second. Just moments later, Galileo detected a fireball peaking at 42,700 degrees Fahrenheit, while Hubble witnessed a mushroom-like plume rising as high as 1,900 miles. For days, the impacts continued as, one by one, the fragments of Shoemaker-Levy 9 collided with Jupiter's atmosphere. Altogether, they smashed into the planet with the force of 300 million atomic bombs, thousands of times more powerful than humanity's entire nuclear arsenal. This power is comparable to the impact that is widely thought to have caused the death of 3/4 of all life on Earth, including all non-avian dinosaurs, about 66 million years ago. They created huge plumes between 1,200 and 1,900 miles high and heated the atmosphere to temperatures as hot as 53,000 to 71,000 degrees Fahrenheit. Perhaps most notably, the impacts left behind dark, ringed scars on Jupiter's clouds. For months, these scars were even more visible than the legendary Great Red Spot. The impacts concluded on July 22, 1994, as Fragment W was the final piece to meet its end in the clouds of Jupiter. Through studying the impacts of the fragments and their aftermath, astronomers were able to learn a lot about Jupiter that they otherwise couldn't have. They created plumes of material from Jupiter's lower atmosphere, similar to the splash that you see when you throw a pebble into a lake. The splashbacks scarred Jupiter's atmosphere with clouds of dark impact debris. This debris acted as tracers of the winds in Jupiter's stratosphere, allowing astronomers to measure the planet's high-altitude winds for the first time. Jupiter's northern hemisphere experienced intense auroral activity, showing that the planet's magnetosphere was influenced by particles from the impact. Comparing these changes to ones in the atmosphere allowed astronomers to study the link and connection between the two. For months, the dark scars on Jupiter were visible until the planet's winds eventually swept them away, dispersing the impact debris. To date, the marks of Shoemaker-Levy 9 remain the most prominent temporary feature ever seen on Jupiter. The impact scars from Shoemaker-Levy 9 disappeared many years ago, but that doesn't mean all of its effects have faded. When Galileo arrived at Jupiter, it imaged ripples in the planet's main ring in 1996 and 2000. Following the comet's impact, the entire ring had tilted by about 1.24 miles. Then, in 2011, nearly 2 decades after the impact, the New Horizons spacecraft, which was on its way to Pluto, still detected disturbances in the ring. Additionally, water from Shoemaker-Levy 9 was still present in Jupiter's atmosphere as late as 2013. Aside from these details, though, Jupiter experienced no permanent effects from the impacts. It came out on the other side completely unscathed, and if we hadn't been there to witness it at the time, we might never know the impact happened at all. Collisions between celestial objects were way more common in the early solar system. In fact, comet impacts are probably the main way that elements other than hydrogen and helium made their way to Jupiter. But today, impacts such as that of Shoemaker-Levy 9 only happen every few centuries. This event showed that large impacts, though far less common, still occur in the solar system, and it was a factor in NASA's decision to develop programs addressing the risk of an impact to Earth. The 1998 releases of the movies Armageddon and Deep Impact, both of which center around large objects threatening Earth, also helped to bring awareness of the dangers of asteroids and comets to the public. To this day, searches for near-Earth objects continue, and there has even been research into how to protect our home planet from impacts by outside objects. You may have heard of the Double Asteroid Redirection Test, which was a NASA mission to fly a spacecraft directly into an asteroid to test how effective such technology would be at protecting Earth from an incoming object. In addition to our own technology, though, there's kind of a built-in defense system for Earth, right in our very own solar system. And it's Jupiter. The impacts of Shoemaker-Levy 9 were neither the first nor the last times that Jupiter was hit by another object. Today, astronomers know that impacts on Jupiter are actually fairly common. We've seen evidence of such as recently as 2020 and 2023. Even if none are as big and spectacular as Shoemaker-Levy 9, our solar system's biggest planet is still taking a lot of hits. For eons, possibly as long as the solar system has existed, Jupiter's size, mass, and incredible gravity have drawn in and consumed comets and asteroids. This has removed many objects that could have ravaged the inner solar system and eliminated even the slimmest chance of complex life ever arising on Earth. The emergence of life on our planet resulted from a large mix of seemingly infinite factors. But one of them was Jupiter's ability to redirect other objects that could have posed a threat to Earth. And the comet Shoemaker-Levy 9 was a spectacular display of Jupiter's ability to act as a guardian.